Hey everybody. Hey, I just want to go over this homework assignment with you, the ones that we did not get to go over in class yesterday. Yesterday we were talking about the grapefruit falling from the tree and how far does it fall. And there are a few different ways uh, we could we could go about doing this. One simple way is with the kinematics equation, like so. Uh, and part B said, what was the speed when it hits the ground? Well, there's a kinematics equation that makes that pretty easy too. If I know that the initial velocity was 0 and the time is 0.75 seconds, and now this time I do want to know the final velocity, I can go over on my formula sheet and I can say final velocity equals initial velocity plus acceleration times time. And so I would say that that's 0 plus negative 9.8 meters a second square times 0.75 seconds. Whenever you put that into your calculator, you're going to get a negative 7.35 meters per second for that instantaneous final velocity. Now, they ask for the speed, so the speed is the same, instantaneous speed is the same as the instantaneous velocity's magnitude. So we'll just leave that sign off. On number 118, a hot air balloon is ascending at a rate of 7.5 meters per second when a passenger drops the camera. So everything in the system is ascending at that rate. So everything has a velocity, initial velocity of positive 7.5 meters per second, including the camera, which this problem is about. It says the camera is 25 meters above the ground when it's dropped. So the camera's initial position, x naught, and sometimes I don't list that, but I am this time because they're telling me that specifically, is 25 meters. How much time does it take for the camera to reach the ground? Now think about what the camera does, everybody. The camera is here, it's moving up at 25, it's dropped, but it doesn't just start immediately getting closer to the ground. Actually, it has to go up, just like any ball that you'd throw. It has to go up a little bit until it finally stops, and then it comes down and speeds up and finally hits the ground. So the nice thing is the equations take all that into account. So if I want to know how much time it takes to get that location of a 0, which we're calling this is 0, this was 25 meters up. Well, how would I do something like that? Now, the one-stop shopping way to do this is to say delta y equals VOT plus a half AT squared. Now, you might not be excited to do this because it's going to be a quadratic. So I have, in retrospect, I'm going to make those y's. Okay, y equals 0 because it is a height. I'm sure that probably confused some of you. Sorry about that. The delta y is going to be the final minus the initial, so that's going to be 0 minus 25, or just negative 25. Then that's going to be equal to an initial velocity of 7.5 t, and then acceleration is negative 9.8. If it's okay, I'll just put in half of that right here, and I'll make that negative 4.9 t squared. Okay, so now we got to solve for t, and there are lots of ways to do this. You could graph the parabola that this equation is for. You could see where it crosses the x-axis. It's one way you could do it. But probably a way that everybody is pretty much familiar with is to make this say 0 equals 4.9 t squared minus 7.5 minus 25. And then this will be the A, this will be the B, including the negative, and this will be the C, including the negative. So now what I'm going to do is I'm going to make that say, I'm going to make this T equals negative B plus or minus the square root of B squared minus 4AC all over 2A. Now, yeah, I know, that's a mouthful, but We can handle this. Negative 7.5 is just 7.5. Plus or minus square root of 7.5 squared minus 4 times 4.9 times negative 25. Okay, and then all of that is going to be over 2 times 4.9. Okay. So then you're just going to go ahead and put that into your machine. Now, when I put that in, I ended up getting two answers. I got a time of 3.15 seconds, which is the one we want. I also got a time of negative 1.62 seconds, which is the one we're going to reject. And so there's how much time it takes to hit the ground. And now that I've done all of that, part B is pretty simple. What's the velocity just before it lands? So it's going to be coming down, and it's going to be coming down pretty fast. I can figure it out pretty easily by saying final velocity equals initial velocity plus acceleration times time. So initial velocity was positive 7.5. Acceleration is negative 9.8. And now we solve for that time of 3.15 seconds. So when I put that in there, I ended up getting negative 23.27 meters per second. This was just significant to the ones place here. So this is only going to be significant to the ones place. So I'm going to make that negative 23. If you notice, they did ask for the velocity. So I'm not going to drop off that negative. I'm going to leave it there. Now on 122, you're supposed to choose which graph goes for which ball. Ball A is dropped from rest. Same time, ball 2 is thrown upward with initial velocity. And say which one is which. Now, we did something like this yesterday in class, if you can remember. For the ball dropped from rest, I have to pick one of the ones that start from 0. So the only ones that could possibly be are 3 and 4. So this I need this to be I need ball A's velocity to start off at 0, so that's it. Now, the velocity changes linearly. We know that if we're going to drop ball A, well, at time equals 0, it's not going anywhere. But at time equals 1, then it's going negative 10, and at time equals 2, it's going negative 20. Use negative 9.8 if you want. But the steps between these are always the same, little g's. And so my point is, this number 4 that curves is not going to be it. That's saying that you're adding different amounts each time. But you're not. You're adding the same amount each time. So 3 is the one that works for ball A. Now, along those lines, and no pun intended, but along those lines, for ball B, now they say here, and I almost never do this because this is confusing, but it says let's make down positive. So in that case, the velocity A would have actually been positive, and that's why that 3 works well for it. Same deal. So we're going to give it an initial positive velocity. And so I'm going to say it's the only choice, right? All 1 and 2 and 5 all have that. Now, the one that I want is going to have the same slope as the one I chose for number 3. Because I don't care if you just drop a ball or if you throw the ball up, it still is changed by gravity the same amount every second. So gravity affects both of them the same. Doesn't matter if one was initially moving and one wasn't. So 2 is the one I'm going to choose here because it is parallel with what I chose for number 3, because gravity affects everything the same. Number 24 is a pretty neat one. So a carpenter drops a hammer from the roof, and it falls down past these windows. The windows are the same size and all, and it asks, is the increase in speed of the hammer as it drops past window 1 greater than, less than, or equal to the increase in speed as it drops past window 2? So what they mean by this is when the hammer was up here just at the beginning of window 1, it has certain smallish speed. And then whenever it was down here, it picked up speed, and so it's faster. Now, by the time it gets down to the top of window 2, it's even faster yet. And by the time it gets out of window 2, it's as fast as we've had. That might be a little exaggerated. Maybe like that. Okay. Now, we know that gravity gives 9.8 meters per second every second. But the thing is, the seconds aren't the same. See, here we have a slowish average velocity. Why? Well, because it's two pretty small arrows. Here we have a way larger average velocity. Why? Well, because it's two larger arrows. And so the smaller velocity means you're going to take longer to cover that distance, versus the bigger velocity means you're going to take less time to cover the distance. So if gravity gives you the same amount of increased speed every second, well, it's more seconds at the top. So you'll gain more speed. So more time means more gain. And less time means less gain. So I'm going to say that increase in speed in window 1 is greater than. And I hope I just gave an explanation. Let's see what they say. Choose the best explanation. The greater speed at window 2 results in a greater increase in speed. No, I just tried to say that it didn't. Constant acceleration means the hammers have the same. Constant acceleration means every second will be the same, but the seconds aren't the same. And the hammer spends more time dropping past window 1. Bingo, that's the one. And the last one, 125, is also a pretty neat one. It goes along with that hammer. So here's the velocity versus time graph for that hammer falling. You can see it's going up into the first quadrant, so they must be saying that down is positive, which I know is again, a little weird, but that is what it is. It says, notice that the times when the hammer passes the two windows is indicated by the shaded area. So like this is where the hammer was at the top of the first window. Here was when the hammer was at the bottom of the top window. Here's when the hammer was at the top of the bottom window, and here's the bottom of the bottom window. And I don't want to say I told you so, but I did say that it took longer in front of the window, the top window, because you were going slower. And you can see something here too. Not that I want to beat a dead horse, but right there is that increase in velocity that the hammer got in the first one, and here is the little baby increase in velocity that it got in the second one. Just wasn't that much time. So now they say, what about is the area? Is this area right here? Is that bigger than this one, smaller, or the same size? Well, remember, on a velocity time graph, the area represents the displacement. So if this is the time in front of that window, then this is the displacement that the hammer had in front of that window. So this is the height of the window. And this one is too. If this is the time that it was in front of that window, then this is the height of that window. And they told you that the windows are the same size. I mean, of course they are. They're on the same building like that. So is the area the same? Yeah, because the areas represent the displacement, and the displacements happen to coincide with the size of the windows. And why is that? Because the windows are the same size. That's why.